Hello and welcome. My name is Logan and this presentation gives an overview of my work in the 2020 Google Summer of Code, which I completed at the CDLI under the mentorship of Max Ionoff. The goal of this work was to extract information from Sumerian accounting tablets to make the content of these documents more approachable to non-experts and more amenable to quantitative research methods. This work was motivated by the fact that the CDLI data contains a vast amount of numeric information in the form of administrative accounts recording quantities of various goods. The numeric nature of this data makes it particularly amenable to statistical analysis and other kinds of quantitative research. It's natural to ask, for example, which commodities are recorded in the largest amounts, whether a commodity's distribution is unimodal or bimodal, and so on. But, at present, this analysis is challenging, because the data are recorded using Sumerian numerals. So, for example, if a document records a count of 250 sheep, this will actually be written as 4 gesh 1 u, meaning 4 times 60 plus 10. This notation is opaque to readers who are unfamiliar with Sumerian metrology. Even readers who are familiar with the notation may be slowed down by the need to perform this conversion, which is not always straightforward. It is certainly not feasible to perform any large-scale quantitative analysis without first converting the data to modern notation. For this reason, our project began by developing an automated conversion from Sumerian numerals to Arabic numerals. At its core, this conversion is simply a dictionary, which maps Sumerian signs to their modern values. However, there are a few peculiarities of the Sumerian notation which make this process difficult. The value of a sign may depend on context. So, for example, 1 dish means 1 in most cases, but when followed by gin, it means 1/60th. In longer strings, we may need to identify the boundary where we stop using one reading and start using the other. Sumerian also uses multiple different number systems, which have some signs in common with one another, but which use different bases and assign different values to the signs. For this reason, numeric notations can be ambiguous. Returning to the example of 1 dish gin, we claimed that this equals 1/60th, which is true in most cases, but when counting bricks, it actually means 12. Because of complications like this, when our conversion encounters an ambiguous number, it produces a list of possible readings, where each reading is labeled according to the number system which produces it. This ensures that users are aware of the potential ambiguity, and allows them to choose the correct disambiguation based on the context that the number came from. The conversion also supports subtraction, written using la in Sumerian, and small fractions, recorded with the circumfix gal. Now that we are able to process the numerals automatically, we're interested in knowing what is being counted in these texts. In some cases, this is straightforward. For example, in 1 gesh 5 dish udu, udu meaning sheep is the only non-numeric word in the line, so presumably that is the object being counted. But this logic doesn't work in a case like Tuban Dumunita, which naively looks as though it's recording 20 liters of male children. Obviously, this doesn't make sense, and in fact, this is counting an amount of barley allocated to the male children. The barley isn't mentioned explicitly in this line, however, and must be inferred from context. We also need to account for longer strings, such as this example, where we have an amount of pure large garlic. We want to identify garlic, shum, as the counted object, but we would also like to know that the garlic is pure and large, tsikil and galgal. To properly identify the counted objects, we use a rule-based system. Unfortunately, there is no supervised data available to train a more versatile machine learning model, and linguistic resources for Sumerian are limited, meaning we can't simply derive this information from, for example, a dependency parser. We use a variety of rules to identify counted objects, the simplest of these being word order. In Sumerian, the adjective usually follows the noun, meaning that the word directly after the numeral tends to be the counted object, and any descriptors will probably come later in the line. As simple as this rule is, it's sufficient for many cases. However, it falls apart in examples like the one on the slide. Here we have the word bahul immediately following a numeral. If we naively say that everything after a number is a counted object, we will make a mistake, since bahul in this context is a verb. This tells us that we should be taking part of speech information into account, which we accomplish by scraping the Electronic Pennsylvania Sumerian Dictionary. This lets us translate individual words into English, and project part of speech tags from the English definitions. We can then limit our proposed commodities to words that are labeled as nouns. We also have a set of rules surrounding determinatives. Many Sumerian nouns are written with a determinative specifying the material they're made out of. This allows us to easily recognize items made of wood, metal, and reeds, as well as some categories of animal, such as fish. Such items are all commodities which are likely to be the counted object when they occur in a line. For words which are not written with a determinative, we use WordNet to find hypernyms of the word's English definition. We label some synsets as likely to be commodities, such as foods, clothing, and metals, and others as unlikely to be commodities, such as people and places. We use all of these features to construct a feature vector for each word in a sentence, and we use these feature vectors to jointly classify the words according to whether or not they are counted objects. At this point, we're able to automatically interpret the numbers and determine what objects they're counting. This opens a wide range of avenues for analysis. We developed a variety of visualizations intended to show off the possibilities, but these are by no means exhaustive. The visualizations are grouped into 5 components, which are included as part of the CDLI framework. These include a histogram, which shows an item's overall distribution, alongside summary statistics about the item. This gives an overview of the item's distribution and allows the user to identify features such as multimodality. We also have a similar items display, which lists the objects whose distributions are most similar to that of a given item. This can reveal sets of items which are used in similar ways, such as sheep and goats. The concordance view shows an item in context, and allows the user to identify which uses are most common, and in what contexts an item is counted in particularly large or small amounts. The nearby items view shows other items which are counted in tablets containing a certain object. This information can be displayed as a graph, where nodes represent counted objects and shorter edges represent more common co-occurrences. Cliques in this graph can be used to identify administrative subgenres, such as this clique of fish, beer, oil, flour, and dates, which derives from lists of goods delivered to festivals. Finally, the descriptors view shows words which are used to describe a counted object. Once again, we can construct a graph where edges represent common collocations. Doing so can reveal different use cases for an object, as in this example of words describing goats. Terms relevant to garment production occur separately from terms related to feeding, suggesting that the goats in these accounts can be divided into 2 main categories, those used for meat and those used for their wool. Although we've been able to extract and visualize interesting information about these accounts, there remain avenues for future work. We are limited by the quality of the definitions in the EPSD, which sometimes reflect obscure or uncommon meanings for a word. Better resources would improve the quality of the commodity identification. Furthermore, now that we have labeled some of the commodities in the data, this labeled data could be used to train a more robust machine learning model, to remove the need for the brittle rule-based system currently in place. To wrap up, this work has presented tools to convert Sumerian numerals to Arabic notation, to extract information about counted objects in Sumerian accounting tablets, and has produced a visualization interface to showcase potential uses for this information. Thank you for your attention, and a special thanks to the CDLI and to my mentor, Max Ionoff.